Hi, this is problem set number 3, problem 8. A certain ideal gas has molar heat capacity at constant volume CV. So I've got an ideal gas with a molar heat capacity at constant volume that we'll call CV. Okay, capital C, subscript V. A sample of this gas initially occupies a volume V0 at pressure P0 and absolute temperature T0. So in my initial state, okay, I have, actually I'll call my initial state state 1, okay? So at state 1, I have a volume of V0, a pressure of P0, and a temperature of T0. And that's absolute temperature. Okay? The gas expands isobarically to a volume of 2 V0, and then, okay, let's pause there. So at state 2, we expand isobarically. So what does that mean? That means we have a constant pressure process. So that means P2 is equal to the same pressure at state 1, which is P0, okay? And we know that V2 is equal to 2 V0. That's what it's given in the problem. Okay, so that's what's given so far for state 2. All right, and then it says, and then it expands further adiabatically to a final volume 4 V0. So now we've got state 3, right? And from state 2 to state 3, it was an adiabatic process. So heat transfer is equal to 0, right? No heat transfer because adiabatic process. Okay. What else is given? Oh, okay, it's also given that the final volume, or the volume at state 3, is equal to 4 times V0. All right, that's pretty much all they really give us. So we can start. For part A, draw a PV diagram for the sequence of process. Okay. So this is the givens right here. Okay. And so part A, I'll put that right here. Part A, we need a PV diagram. So this is pressure, and this is the volume, okay? At state 1, I know I have V0, P0, T0. At state 2, I have an isobaric process where the pressure remains constant, but the volume doubles, right? And to get from state 2 to state 3, I go through an adiabatic process, and then the volume increases even further to 4 V0, okay? So let's draw that. So at state 1, I have V0, right? 3 V0 and 4 V0, okay? And then I've got P0 right there, okay? Move that closer a little bit. P0. Okay. So for state 1, I'm at V naught, P naught. So going up and here. Okay. So state 1, I'm right here at P naught, V naught. That's my state 1. I'm going to use this color. That's my state 1. Right. So V naught if I go all the way down, and P naught. Okay. At state 2, I'm still at P naught because P2 equals P naught. Right? That's what it says right here. But the volume doubles. V2 equals 2V naught. So I go from there to 2V naught, still at the same pressure, P naught, and that is my second state. Alright. And from state 2 to state 3, I go through an adiabatic process where the volume expands further to a final volume of 4V naught. So somehow I need to end up here, right? Okay. So I guess I'll draw my path between state 1 and state 2 first. I went from state 1, went to state 2 this way, and the pressure was constant, as you can see. The volume doubled. From state 2 to state 3, I had an increase in volume again, but this time I went through an adiabatic process. It'll look something like a curve, right? Like that. Okay, and I hit 4V naught. The pressure wasn't given for P3, so I'm not sure what that value is. But I could certainly find that out, right? So from chapter 19, section 8, adiabatic process for ideal gases, we have that formula. And I'll use the color, I'm going to use the color blue for all our side quests to find various things. So to find, I have this formula right here. P1 V1 gamma is equal to P2 V2 gamma. And I could use that for all adiabatic process for an ideal gas, right? I could use this equation. Okay. So by the way, gamma is just the ratio of molar heat capacity. So gamma is equal to Cp over Cv. Okay. That's what gamma is equal to. But in this process, we're not looking for, the adiabatic process is actually from state 2 to state 3, right? This is state 3. So I will use this formula for what I'm looking for. So instead of P1 and P2, I am looking for P2 and P3. Okay, so, oops. So the pressure at state 2 times the volume at state 2 to the gamma, to the power gamma, is equal to the pressure at state 3 times the volume at state 3 to the gamma. Okay. What do I know? I know that P2, so now I'm going to plug in my knowns. P2 is it's given right here. Okay, and V2 is just 2V naught to the power of gamma. That is equal to P3, which is what I want to find, times the volume at state 3, which is 4 V naught, that's also given, right, to the power of gamma. So from here, I can look for the pressure at state 3. P3 is equal to P naught times times 2 volume naught to the power of gamma over 4 volume naught to the power of gamma, right? And that I could just write as P naught 2 V naught over 4 V naught to the power of gamma, right? And then I could cancel stuff out, mainly my V naught and 2, this becomes 2 and this becomes 1, right? So then I'm left with P naught times 1/2 to the power of gamma as my pressure at state 3, okay? So we've just found our pressure at state 3. And we might need to use that later, so I'll just hold on to that. But anyways, now I can write down my pressure at P3. This is P3 equals P naught times 1/2 to the power of gamma, okay? This is an equal sign. Let's fix that. P3 equals P naught times 1/2 to the power of gamma, okay? So that's what we found. Okay. So that is the answer to part A, right? The PV diagram, and we listed down the pressure and volume based on P naught and V naught, which were given, okay? So moving on, let's go to part B. Just put a little thing there, okay? So part B. Compute the total work done by the gas for the sequence of processes. So when we say work done by the gas, we're looking for the work done by the system, right? Because the gas is the system in this problem. So if we are looking for the work done by the gas or work done by the system, we will have to add, as you can see here, we have the work done from this isobaric process from state 1 to state 2. And then we'll have to add it to the work done by this adiabatic process from state 3. Okay? So that will equal to work, oops, let me first remove those highlights. Okay. All right. So work done by the system from 1 to 2. I'll just rewrite that as 1, 2 for simplicity. Plus work done by the system, or work done by the gas from state 2 to state 3, right? So we have to find two things here. All right, I'll start with the work done by the system from state 1 to state 2, okay? So work done by the system from state 1 to 2, which is an isobaric process, right? It's a horizontal line. That's quite easy to find. I just need to find the area of this rectangle right here. Right, and that's a great thing about an isobaric process. When you have constant pressure, the work is just the area under that curve, right? Okay, so Work done by the system from state 1 to state 2 is equal to, what is the height? The height is P naught times the width, which is 2V naught minus V naught, okay? That's these guys, from 2V naught to V naught. This is the width, and this is the height, is P naught, right? Then that gives us the area. Okay? And we could simplify that, so that is just P naught times 2V naught minus V naught is V naught. So the work done by system from 1 to 2 is P naught over V naught. Okay? I'll use green to mark that so I could find it later. All right, what about the work done by the system from state 2 to state 3? So now we're moving on from state 1 to 2, and now we're looking at state 2 to state 3, which is an adiabatic process, right? All right, so for an adiabatic process, remember that heat transfer is equal to 0, right? So if we plug in our first law of thermodynamics formula, which is the change in internal energy or thermal energy is equal to heat transfer minus work done by the system, right? Well, it's adiabatic, so right away we can say that heat transfer is equal to 0. Q is equal to 0, right? And we stated that right here. Q is equal to 0. No heat transfer for adiabatic conditions. All right, so that makes it pretty easy. We'll be left that the work done by the system is equal to the negative change in internal energy, right? Or thermal energy. Those are interchangeable, so you might hear me use them interchangeably. Okay, what else do we know? We found out in chapter 19 that this case is always true, right? For an adiabatic process, for an isothermal process, for an isobaric process, or for an isochoric process, you know. So if your pressure is constant, if your volume is constant, if your temperature is constant, in any process, we should know that, again, this is a side mission, but the change in thermal energy is always equal to the number of moles, N, times the molar heat capacity for constant volume, CV, times the change in temperature, okay? That is always, this is always true. So true, always true for any process. And when I say any process, that means whether you have constant pressure, right? If it's isobaric, or constant volume, isochoric, or constant temperature, isothermal, you can always use this formula, okay? So now that I know that, I could plug that back in here for my change in thermal energy. So I would get that this is equal to, don't forget the minus sign, so negative N CV delta T, right? Okay, I want to end with whatever values they gave us. So all our answers should come with these given values, because these given values we assume to be a number, right? So that's how I'd like to end my problem. They didn't give me any temperature other than T naught, so I'm not going to leave it as delta T. I'm going to leave that all my answers should be within the given variables, V naught, P naught, T naught, okay? And CV as well, because CV was also given. All right, so they didn't give us a number of moles in this problem, I don't believe, right? So what's another way I could write moles? Okay, another side mission right here. So this was our first side mission for part B, and this is our second side quest for part B. Let's remember the ideal gas law, right? And that is PV equals nRT. Since we're dealing with an ideal gas here, we could use this. Okay? And from state 2 to state 3, it is an adiabatic process. So basically, the only constants here are really just the number of moles and the gas constant R. Because temperature changes, volume changes, and pressure changes, right? So because of that, I could say that PV over T is equal to the constant nR. So in that case, P2, V2, and T2 is going to equal to this constant nR, which is also equal to P3, V3 over T3, right? Because they're always equal. Okay? So that is equal to nR, the constant nR. Now I can solve for n because that's what I'm looking for. That's what I would like to replace in this problem. Okay. So looking at this, I got P2 V2 over T2 equals nR. So I could say that nR or n is equal to the pressure at state 2, the volume at state 2, over the temperature at state 2 and R. Okay? So I'm going to replace n with that. Okay? But also I don't know what is my delta T, actually. That's another thing, right? So now I've got negative n CV. I could get rid of this parentheses. So negative n CV, and delta T is really what? In this case, we go from state 2 to state 3, so that's temperature at 3 minus the temperature at 2. Okay? So now I have my value for n. And do I have my value for T2? I don't have my value for temperature at 2 or my temperature at 3. Right? So I would have to look for those as well. Okay, so again, we have the value for CV that was just given, right? They called it CV. We're looking for what value of n we could have in terms of P naught, T naught, and V naught, as well as the value for temperature and at state 3, and temperature at state 2 in terms of those P naught, V naught, and T naught. Which reminds me, actually, this is not in terms of P naught, V naught, and T naught, so I have to keep going. Actually, n is going to be equal to, well, P2, we said here, is equal to P naught, right? And V2 is equal to 2 V naught. So at least we have that. P naught times 2 V naught, that is the value for V2. I also don't have my temperature at state 2, so I have to find that. So we'll have to get back to this, actually, side quest, another side quest, number 3, to find my T2. So then I can plug that in here for n. Okay, so to find my temperature at state 2, what do I know? I'll use my ideal gas volume, PV equals nRT, okay? From state 1 to 2, I have an isobaric process, right? This is constant pressure. So let me just clarify that this is from state 1 to state 2. Okay, so for this process, what do I have as my constants? Isobaric process, P is constant, N and R are also constant. So I'll have V over T is equal to NR over P. And again, these guys are constant, right? So therefore, my V at state 1, or V naught over T naught, would be equal to my volume at state 2 and temperature at state 2. So then I could rewrite that as state 2 is equal to V2 T naught over V naught, right? And I'll plug in my knowns. I know that my volume at T2 is twice my V1. Okay, so really that's all I need to know. So that is 2 V naught times T naught over V naught. And my volume naught would cancel out. So then I'm left with temperature at state 2 is equal to 2 T naught. Okay. So I could plug that in back to our second side mission. And instead of using this T2 right here, I'm going to use 2 T naught. That way, my answers are all in the given values, P naught, V naught, and T naught. And CV if I want to, because CV is also given. All right, we could cancel some stuff out here. Cancel out the 2. And we are left that N is equal to P naught V naught over R T naught. Okay? Yeah, we had 3 side missions so far. And we'll have a lot more in this problem. Well, maybe not a lot more, but we have some side missions to do. Okay, so now I have my N, my value for N, and my value for T2. Okay, so now I have N, I have CV, and I have T2. Now I still need to find the value for T3 so that I could find this. I could write everything down in terms of our givens. Okay, so how do we get T3? Well, another side mission, of course. So side mission number 4, to find the value of temperature 3. Okay, I know that, let's just clarify. So for this one, to find T3, I have to look at the process from state 2 to state 3, which is an adiabatic process, right? Okay. For an adiabatic process, what can I say about the ideal gas? What is constant here? Adiabatic, really just N and R are constant, right? Yeah, because T changes, volume changes, and pressure changes in adiabatic. Okay, no worries. So that just means that the pressure at 2 times the volume at 2 over the temperature at 2 is equal to the constant NR, right? And since it's constant, NR doesn't change, that means the pressure at 3 times the volume at 3 divided by the temperature at state 3 is also equal to that constant. Therefore, this is equal. The pressure times volume over temperature at both state 2 and state 3 are equal. Okay, so now I will write this in terms of T3. I'll rearrange this in terms of T3. And that would be P3 V3 T2 over P2 V2. Right. Okay. Did I find my P3 earlier? I did, right here. All right, so we found our P3 earlier, which is P naught times 1/2 to the gamma. So I'll plug that in. P3 is equal to P naught times 1/2 to the gamma. V3, did I get V3? Yes, V3 was given as 4 V naught. Okay, times 4 V naught, okay, times T2. T2, did we solve for T2? Yes, we did. Right here in side quest number 3. So times 2 T naught divided by pressure at 2, which I believe is isobaric. Yep. So pressure at 2 is the same as P naught, right? Same as pressure at state 1. So that's P naught. And volume at 2 is twice the volume at V naught, right? Okay, so that was also given. Beautiful. So times 2 V naught. Awesome. So now our temperature at state 3, right here, is all in terms of the given P naught, V naught, and T naught, right? Okay. Actually, except for gamma, I just realized gamma is, again, gamma is equal to, what is gamma? Gamma is Cp over Cv, right? So that's the, that is the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. However, in this problem, we were not given Cp, we were just given Cv. So we can't use gamma because we have to use it in terms of CVs only, no CPs. So what do you think that means? If you guessed side quest number 5, you are correct. So let's go to side quest number 5. Okay, so side quest number 5. What do we know about CP? Okay. This is in chapter, I believe this is chapter, I'm looking at my notes right now. CP, CV. Oh, okay. This in chapter 19.7, molar heat capacity for ideal gases. We got the formula that, okay, this is a side formula. Oops, that should be minus R. So we have that the molar heat capacity for constant volume is equal to molar heat capacity for constant pressure minus the gas constant R. Okay, so then we could solve for Cp, and that's just equal to Cv plus R, right? Because this, we can use this because this was given to us and R is a constant. It never changes. We should know the value for that. So we can use that. So now gamma is equal to, instead of Cp, I'm going to use Cv plus R for Cp, right? Okay, so it's going to equal to CV plus R over CV, which is equal to 1 plus R over CV. That will be my value for gamma. Okay, I told you guys there was quite a few side quests. Alright, so let's move side quest number 5 lower a little bit because we'll have to return to side quest number 4. So then my T3 is equal to P naught times 1/2 to the power of, instead of gamma, which involves CP that I cannot use because it wasn't given, I'm going to use this for gamma. 1 plus R over CV, because CV was given and R is a constant. Okay, so to the power of 1 plus R over CV. Okay, and multiplied by 4V naught times 2T naught over P naught 2V naught. And I could cancel things out. What did I use to cancel out? I used pink to cancel out. Okay, so stay consistent. So I could cancel out my P naught, 2, and V naught, right? So then I would be left that T3 is equal to, oh, I could also cancel this out. 4 and 2. Wait, can I? No, I don't think I can because there's a power right there. Okay, never mind. So my T3 is equal to 4 T naught times 1/2 1 plus R over CV. Okay, move that a little lower because it's a little too close. And then I find T naught in terms of our given values T naught and CV and the gas constant R. Okay, so we've finished side quest number 4. And we actually had to go to side quest number 5 to go back to side quest number 4. Anyways, going back to part B, now we know T3. Okay, so now we've got T3, and we can now solve for work of the system from 2 to 3, from state 2 to state 3. Okay. All right, so this is equal to, I'm just going to bring this down here so for more space. N is P naught V naught over R T naught. Right, that's N. Oh, don't forget the negative, so minus. You know what? Instead of having that minus, I'm gonna multiply that negative into this parentheses, so it will be T2 minus T3, right? I just multiplied everything that's in the parentheses by this negative so that I could get rid of that negative outside. All right? Okay, so I've got my N. Okay, and then I need to find my CV, or I don't actually because that was given to us. And then I need to multiply that by T2 minus T3, which is 2T naught minus, what is T3? Minus 4 T naught times 1/2 to the power of 1 plus R over CV. Okay. Oh look, I could also bring stuff out here. because both of these, let's use a different color. Let's use, I guess, light blue. Both of these terms have T naught and 2 and 4, right? So I could actually bring that out. Let's do that. So that is equal to P naught V naught over R T naught times molar heat capacity for constant volume times 2 T naught. And then that would just be 1 minus 2 times 1/2 to the power of 1 plus R over CV, right? Again, I just have to multiply this to both terms, and then I would end up with these guys again. So I just factored 2 T naught out of this guy. Okay. So what can we cancel out here? We can cancel out T naught, right? Yeah, we could cancel out T naught. So canceling out T naught, I am left with my work done by the system from state 2 to state 3 is equal to P naught V naught CV over R. Actually, I also have a 2 right there, so 2 P naught V naught CV over R multiplied by 1 minus 2 times 1/2 to the power of 1 plus R over CV. Yes, we got there. We've got the work done by the system from, let me just make that a little neater, from state 2 to state 3. Nice, guys. And remember, what we're really looking for part B is the work done by the entire system, from all the way from state 1 to state 2 to state 3. Okay? So in order to get that, we have to add work done by the system from state 1 to 2 plus work done by the system from state 2 to 3. And we already have the values for both of these, so at this point we just need to add them, right? This was our first work done by the system from state 1 to 2, and then add it with the work done by the system from state 2 to 3. Okay? So let's do that. So work done by the system totally is equal to work done by the system from 1 to 2, which was right here, right? That was what we solved for initially. Plus work done by the system from state 2 to 3, which is right here. We solved for that too. You may have forgotten that because we had so many side missions to do to get there, but we're there. We're almost done. So work done by the system from 1 to 2 is equal to P naught V naught. And we'll add that to the work done by the system from state 2 to state 3, which is 2 P naught V naught CV over R multiplied by 1 minus 2 times 1/2, 1 plus R over CV. Okay? And we have like terms, right? We have P naught V naught, so we could factor that out. So that will be equal to Oh, yeah. P naught V naught plus, times 1 plus 2CV over R multiplied by 1 minus 2 times 1/2 1 plus R over CV. Okay. And that is the work done by the system. So that is the answer to part B. All right. What are we looking for part C now? Find the final temperature of the gas. Okay. So that's cool. That's part B. So for part C, find the final temperature of the gas, or the temperature of the gas at state 3. Actually, I believe we solved for that earlier in side mission number 4. So the temperature of the gas at state 3 is T3 is equal to 4 T naught times 1/2 1 plus R over CV. Okay. And this is how we solve that. We did that earlier. Okay. That's nice. And now moving on to part D. Find the absolute value of total heat flow. Okay. Q into or out of the gas for this sequence of processes and state the direction of heat flow. All right, so we'll do that. So for part B, find Q of the system, right? From state 1 to state 2 and state 2 to state 3. So total Q would equal to Q from state 1 to state 2 plus Q from state 2 to state 3. All right, well, we can simplify this because we know that this part was an adiabatic process, right? From state 2 to state 3, so Q equals 0. There was no heat transfer between state 2 to state 3, so 0. So now we really just have to find Q from state 1 to state 2. Okay? And remember that was an isobaric process. Yeah, that was constant pressure, right? Isobarically, so constant pressure from state 1 to state 2. That's why pressure 2 is equal to pressure naught, right there. Okay. And I know that for an isobaric process, I believe this is only true for an isobaric process, okay? But for an isobaric process, Q is equal to N Cp delta T, okay? I'll just write this down, that Q 1, 2, which is an isobaric process, is equal to N. Okay, and only true for an isobaric process. Okay. So for an isobaric process, Q is equal to NCP delta T. Okay, not for any other process. You can't do that when it's isothermal or isochoric. Okay, but for isobaric, you can say that Q equals NCP delta T. All right. Again, we can't use CP because that wasn't given to us. So let's look for CP in terms of CV and R, which, we have right here. We did that in side mission number 5. And N, we can't use N because that wasn't given to us, but we could, similar to side mission number 2, we could find N in terms of P P naught, V naught, and T naught, right? Because this was the value for n in state 2. Because P2, V2 over T2 is equal to NR, right? So actually we did that inside mission number 2. So we'll just, at this point, have to substitute in what we already did work from earlier. So N is equal to P naught V naught over R T naught times CP, which is CV plus R. And then delta T from 1 to 2, that is T2 minus T naught, right? Well, what is T2? Because we can't use T2 since that wasn't given. Well, side mission number 3, T2 is equal to twice T naught. So let's substitute that out. So 2T naught, we'll call that, because that is equal to T2, right? And we solved that inside mission number 2 up here. This is how we did that, right? Okay, cool. So this simplifies 2 P naught V naught over R T naught times molar heat capacity through constant volume plus R, and 2 T naught minus T naught, that just equals T naught. And looks like I can cancel out my T naught. Okay, so then I am left with, oh, actually I'm also gonna divide both sides of this equation by R, which comes from here, okay? So that I can simplify even further. So then that would give me is equal to P naught V naught times CV over R, right? Because all I'm doing is I am bringing this into both terms. CV over R plus R over R, or actually that is just equal to 1, right? So then that is my answer for Q1 to 2. My heat transfer from state 1 to 2 is P naught V naught times CV over R plus 1. And again, that is also equal to the heat transfer of the entire system, right? Because Q from 2 to 3 is adiabatic, and that's 0. So I can say that Q is equal to Q from state 1 to state 2, and that is equal to this right here. All right. Hope that helped.